Hello, welcome back. I believe this is lecture number 4. Today we're going back to game theory. And today is a very special episode because I have never seen someone actually solve this particular problem before. So as far as I'm aware, this is a brand new theory that we're putting out here. And today's topic is Kaiji Ultimate Survivor. This is a very fun, very cool gambling show. And in particular, it focuses on certain puzzles that the main character is trying to solve. Very high-stakes gambling of you either make it out with a couple million yen or you lose your life. So today's topic is going to be a game that they introduce in, I think, episode like 2 or 3, and it's called Restricted Rock, Paper, Scissors. I recommend watching the series, obviously, but today's topic is just not necessarily going to be on the plot points, so there is going to be zero spoilers, but just on the mechanics of the game, which is honestly more important than any sort of plot element. But I'm not here to do literary criticism. I'm here to explore some game theory and some fun scenarios. So, the rules of the game presented are, it is a game of rock, paper, scissors, but it's not quite that simple, or else there'd be no point in doing game theory analysis on it. It is roughly 100 players. We'll do that for simplicity's sake. And the winner is the person with the most points. Again, I'm roughing out some things that happen within the show just for simplicity. But we'll say that the winner is the person who gets the most points. You get 1 point for winning, 0.5 points for a tie, and 0 to lose. What I mean by tie is paper, paper, that's a tie. And it is restricted rock, paper, scissors. So you can only play rock 4 times. You can only play paper 4 times. You can only play scissors 4 times. So a total of 12 games of rock, paper, scissors are played for every single person. Now, obviously, this means that not everyone's going to play against each other, and so it's generally a field of everyone playing rock, paper, scissors. There's something else that is important, and that is everyone knows how many rock, paper, and scissor cards or actions are left on the field. There is a counter, so everyone knows that there is a certain amount of rocks, a certain amount of papers, and a certain amount of scissors. In reality, this probably won't play too much in our calculations, but it is important that we understand this factor going in. So first, let's look at first, we'll understand to solve this problem, we have to simplify it. And I feel like this is pretty easy to understand, but just go on the rigorous part of it. Whenever we're looking at these complex games of, oh wow, they have 12 options each, there's 100 different players, how in the world are you going to solve that? Well, let's look at a game of rock, paper, scissors between 2 players and 3 actions each. They each have 1 rock, 1 paper, and 1 scissors. Keyboard is broken. Let's have a game between these 2 players, Ritsu and Yui. And whenever they first play, the initial outcome of the game, you have 9 different scenarios. They both play rock, they both rock, paper, rock, scissors, paper, rock, paper, 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 scissors, scissors, rock, scissors, paper, scissors, scissors. However, if you can see within this that those don't all lead to different outcomes. Yes, they have all played different cards, but rock, rock, paper, paper, scissors, scissors all lead to 0.5, 0.5, 0.5. So fundamentally, there's nothing different between those. So we only have 6 different outcomes. And then we re-look at it, and we figure, well, if you win, then there's no difference between winning with rock, paper, or scissors. And so, again, you now only have, you drop another 3 outcomes. And then, once again, if you lose, then it doesn't matter how you lose because each play doesn't necessarily matter. They're fundamentally the same. And so you end up with 3 unique outcomes. You either tie, you win, or you lose. And fundamentally, that's only 2 unique outcomes because it's either you tie or you win. Because losing is going to be the exact same thing but mirrored for the other player. And so let's look. This is game 1. Let's say for our purpose that R played rock, or Ritsu played rock, and Yui played scissors. And I will have to move my webcam for this. There's a lot of tables today. Because of this, we give Ritsu 1 point and Yui 0 points. And from this table, we see that now we have a unique set of options. Because unlike within the first graph, or the first table, every player now does not have access to the same options. If they tied, then of course they would have access to the same options, because inevitably they would both have paper, scissors, or whatever other combination is available. Thus, whenever we look at this, we can say that Ritsu has paper and scissors, while Yui has rock and paper. Well, we'll look at this as if we're looking at any sort of prisoner's dilemma or any other normal form game theory game. And we see that, well, if Ritsu were to play paper, then what would we choose as Yui? Well, we can either lose or we can tie. So if Ritsu were to play paper, Yui would play paper. If Ritsu were to play scissors, Yui would play rock. If Yui were to play rock, Ritsu would play scissors. I'm just looking and seeing which along these horizontal lines comes up with the highest option. Remember, we were talking about this in the Prisoner's Dilemma game. And then for the final one, if Yui were to play paper, then Ritsu were to play paper. Now, whenever you come up with a solution, you might think, wait, hold on a second here. You might end up with no actual solution because, well, there's no Pareto equilibrium. However, this is not inherently correct because there kind of is a more optimized situation. Because if you are Ritsu, you can guarantee that if you play paper, then there is no way for Yui to do. There's no way for you to ever not come out of the scenario with at least some point gain. And so you end up playing paper, and then Yui has to play paper in response. Because if Yui does not play paper and plays rock, well, then you're down 2-0, and there's no way to recover from that, even if you were to win the next one. So thus, if you play paper, then Yui must play paper in response. And so at the end of that, then, so both players play paper, and you end up with 0.5 each. And then you end up with the final game. And this final game is very important because Ritsu, the winner of the first game, the tire of the second, well, they're both tired of the second, is left with scissors, and Yui is left with rock. Therefore, Yui wins the third game. Thus, whoever wins the first game will always lose the third game, and they will always tie in the middle game. Inevitably, what this means is you will always tie in a 1v1 3-action game if it's an unbalanced start. So then what happens if you play rock, or scissors, or paper at the beginning? Well, inevitably, you will just end up in the exact same scenario as this previous one, where you have a mirrored 2x2 grid, and your options are to tie or win, and then whoever, if you tie, then you tie the next game, so it's tie, and that's obviously 1.5. But if you were to win the game, then you end up in this exact same scenario where you will lose the next one. So the best score you could possibly get if your opponent is playing rationally is going to be 1.5. Therefore, leave it there. In rational play, the most available points is 1.5, meaning a guaranteed tie with 2 players and 3 actions each, one of each plays. So what happens if you have 2 players, but you give them double the actions, where they can play rock twice, paper twice, scissors twice? Well, the first move is going to be the exact same. And I will say here that my theory going into this is that deviation from balanced play will cause a loss. Ignore the typo. So, let's map that out. We'll say that in the scenario, Ritsu played rock twice, and Yui in response played scissors twice. This leaves Ritsu with a huge 2-point advantage. And, well then, you're stuck in the exact same situation as last time. If you notice, then you are in this place where they're both forced to play paper twice in a row. And whenever you're both forced to play paper twice in a row, then you get that 0.5, leading with... Oh, I forgot to edit that. But what happens after that is the exact same scenario if you were to play with just the 3 actions. The net gain, the net loss that you come out of is going to end up being the exact same as what happens within the 3 action game. So we're concluding the fact that 6 actions does not make a difference from 3 actions in the course of play. In fact, they mirror each other quite well. And this can lead us to the conjecture of, well, what happens if it's 9 actions? What happens if it's 12? Etc., etc. And that math is very difficult to do. Not because the actual complexity of it, but because purely the long-form writing out of it is going to be more complex and more complex. But because we're able to prove it with this first game and the second game, and the fact that there's no deviation, then it's theoretical. Of course, if someone manages to prove that it's not, then I'll be very surprised. But we find that no matter how many actions you increase, then you're inevitably going to end up with a tie game if you have 2 players. Well then, what happens if you're to have more players and more players? Well, you can actually find out that it's the exact same scenario. See, no matter, even if you have, you're down 2 games and you've played, as long as you play a balanced game, you will inevitably end up with a even point total with the other rational players. The only way to deviate from that is to play irrationally within this sphere in this game. And that's why knowing the total of rock, papers, and scissors on the field is important, because it's the only way to really guarantee that you play an irrational behavior. So a pure random initial play point, as long as you have 3 cards, or sorry, not 3 cards, 3 actions available to you, is important, and then you go into your diagram like that on the bottom right. And so what does that actually mean at the end? Well, if we solve it with more players, we'll end up finding out that the answer of the most amount of points available to you, no matter how many players you have, is the number of actions divided by 2. If we go back to our 3 action game, we end up with 1.5 points, which is obviously 3 divided by 2. And then if we scale it up to our 6-point action, then it's the exact same. We end up with 3 points as our maximum possible outcome, as long as the players are playing rationally. And that is my problem of the day. I really hope you enjoyed it. I will probably... I don't know if I will do any more Kaiji videos, just because the rest of the series doesn't really seem like it's... I don't know, really game theory oriented, and it's more like luck and chance based, and maybe we can do some probability math, and I thought that that's what we're going to have today, but rationality wins in the end. But thank you for joining me on this lecture. I will try to make some non-econ videos in the future, but hey, it's not like anyone watches these to the end anyway.